Okay, today we're going to talk about inverse relations. And notice I didn't call it inverse functions because all of the graphs that we're going to look at today are not necessarily functions. But we have this first function here, and we know this is a quadratic equation, so it's a parabola. It is a function because it passes the vertical line test. But the question that we now want to ask in this lesson is, does this function have an inverse that is also a function? An inverse that is also a function. So that's the question we want to investigate here. And in order to determine that, we need to use not the vertical line test, but the horizontal line test. And so the idea is that if this function does not pass the horizontal line test, then whenever you draw the inverse of it, the inverse will not pass the vertical line test. So basically the horizontal line test is a way for you to determine whether a function has an inverse that will also be a function. All right? So in this case, it would not have a function. It would not have an inverse that would be a function, because even though it passes the vertical line test, which classifies it as a function, its inverse would not be a function because it does not pass the horizontal line test. Okay, let's look at a few examples. Okay, here we have this first example, and the question we want to ask is, first of all, is it a function? So, is it a function? Yes, because it passes the vertical line test. So, yes, it is a function. Now, does this have an inverse that will also be a function? Yes, because it passes the horizontal line test. So, it has both checks. All right, in this second example, yes, it is a function. No, it is not a function because it does not pass the vertical line test. So, no, it is not a function. However, will it have an inverse when you draw the inverse of it, when you switch all the x's and y's? Will it have an inverse that is a function? Yes, because it passes the horizontal line test. So, part 3. Is this a function? Well, clearly it's not a function because it does not pass the vertical line test. And it also doesn't pass the horizontal line test, so its inverse will not be a function either. And then the last one, this is a function because it passes the vertical line test, but its inverse will not be a function because it does not pass the horizontal line test. So pretty simple concept here. Now, a function that a function that passes both the vertical line test and the horizontal line test is a special function called a one-to-one function. So you need to memorize that. A one-to-one function is a special type of function that passes the vertical line test and the horizontal line test. Let's look at an example. Here, it passes the vertical and the horizontal, so this is a special type of function called a one-to-one. Here, this is a function because it does pass the vertical line test, but it's not a one-to-one function because it does not pass both tests. Okay, example 2, we want to find the inverse of this function algebraically. And I'm going to add here also to give the domain of f inverse of x. So we want to include the domain of the inverse function. Now, the domain of the inverse function is the same, equals the range of the original function, because we know that with inverse functions, the x's and y's switch places, which means the domain and range also switch places. So, first thing I'm going to do before I even find the inverse algebraically is I'm going to attempt to sketch this graph. And if I graph this, I'm going to use the idea that I know my vertical asymptote is at x equals -1. So I can draw that vertical asymptote in there. And I can use my coefficients 1 and 1 because the exponents are both 1. So I can use Bosco to figure out that the horizontal asymptote is y equals 1. And then if I plug in 0 for both of these x's, I get an ordered pair of 0, 0. Okay, so you can just see that if I plug in 0 for these x's, I'll get 0 over 1, which is 0. So we know that the graph crosses through that point, so it should look something like this. Now, not that this is critical right now that you know how to graph this by hand, but it does help us write the range. So the range of this function is going to be negative infinity up to 1 in union with 1 to infinity. So if this is the range of f of x, that is going to become the domain of the inverse function. So let me write that down. This is going to be the domain of the inverse function. All right, so it's going to be that. Now, let's see if we can write this equation inverse. So y equals x over x plus 1. Switch the x's and y's. So I'm going to come over here and continue it. X equals y over y plus 1. First thing we want to do is we want to multiply by y plus 1 on both sides. When we do that, we're going to see the y plus 1's cancel out. And that's going to leave us with xy plus x whenever you distribute this x. So xy plus x equals just y. Now remember, the goal is we want to solve this for y. So we've got to get all the y's on the left, and all the terms that do not have a y, we want to move to the right. So negative x. Now this next step is very important, so I want you to put a star around it so that if you see this problem on a quiz or test, you will remember what to do. You've got to recognize that both of these terms have a y. So I can factor out this y. I can factor out the y. And when I factor out the y, I'm left with x minus 1 equals negative x. Now I divide by x minus 1, cancel, and my y, which is my inverse function, is going to equal negative x over x minus 1. And that is essentially how you find the inverse of a function. Next, we want to learn how to sketch inverses if we are given an original function. So the process is called the inverse reflection principle. And basically the idea is that if you have a regular function, f of x, the original function, there should be perfect symmetry between that function and its inverse about the line y equals x. So that means on the right side and on the left side of y equals x, the function should look exactly the same. So I want you to notice the symmetry of the light blue curve, which is our original curve, and the black curve, which is our inverse function, and how symmetrical it is about this red line y equals x. Now, if you're anything like me, you're not the best artist and not the best at visualizing this. So the best thing that you may want to do is simply to pick a few points, maybe that point, and maybe that point, and that point, and that point, and maybe that point. Find the x and y values and switch them, and then replot those values on another graph, and then connect them and make it as symmetrical as you can about the line y equals x. So let's say this ordered pair is 2, 8. Then over here, you would want to be graphing 8, 2, and so on and so forth. In this last example here, we are going to learn what's called the inverse composition rule. And basically, this is the idea that if you are trying to determine whether two functions, f and g, are inverses of each other, what you have to do is you're going to want to take g and plug it into f and get x. Then you got to plug f into g and also get x. If you get x in both of these situations, then you will conclude that f and g are indeed inverses of each other. So let's see if we can prove that algebraically with this example. F of g of x means take this function and plug it in here in place of the x. So I'm going to put a parenthesis. I'm not going to write the x. Instead, I'm going to write the cube root of x minus 1, close my parenthesis, cube it, and then add 1. Now, it's very important here that you don't become the happy magical slasher, as I call it. In other words, don't just do this, slash, 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 slash equals x. If you do that, you will get a big red X. That is not showing the proper steps, so you need to make sure that you show the proper steps in this process. So, the first thing is you have to recognize that the cube root and the cubing cancel. Then you rewrite the equation and you have x minus 1 plus 1. Then you recognize that the negative 1 and the positive 1 cancel. Then you write equals x. Notice I showed 2 steps. So you need to make sure you show the steps. Now let's also do g of f of x. So now we're going to take this function and plug it right in there. So that's going to be cube root of x cubed plus 1, which is this function, minus 1. Now once again, do not just do this, slash, 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 slash. No, that's not going to get you any credit on a quiz or test. Make sure you show your work. So the first thing is that the 1's cancel out. So that's going to leave you with the cube root of x cubed. And then the cube root and the cubing, cube root and the cubing cancel out. And that is what's going to leave you with x. So because you get x on both of those, you will conclude that f and g are indeed inverses. Now the nice thing is we already knew that because it said show it algebraically.